Hello Year 10, here is the feedback from the online lesson that you had on Tuesday, February 9th about internal energy and changes of state. To start with, I asked you to think about which of these three science concepts that we have met before did you feel most confident in. Luckily, all of the topics got a vote, but the majority of you were most confident with the previous work on changes in state. And because of this, I will try and add some more extra recap of the other concepts into future lessons. So we started with a little recap of a concept we met in Year 9. If you weren't here in Year 9 or you feel you have matured since Year 9, then this slide was for you. More energy needs to be transferred to the thermal energy stores for some materials to increase their temperature. Some materials are easier to heat up than others, and specific heat capacity is a way of comparing the amount of energy you need to add to a substance to heat it up by the same amount compared to other substances. One thing that was highlighted on this slide was the letter J, which is the unit for joules, which is what we measure the amount of energy in. So this was saying that you need 4,200 joules of energy to heat 1 kilogram of water by 1 degree Celsius. The next slide was basically saying that if you need a lot of energy to heat something up, then that something will have a lot of energy to give out again when it cools down, and that the amounts of energy are linked to specific heat capacity measurements of the substance that your thing is made from. This slide showed you the equation to work out how much energy needs to be transferred to heat up a substance. And it was a 42% to 58% split, with most of you feeling like you had not worked with this equation before. Luckily, this is one of the equations that is given on the formula sheet in exams, so you do not have to memorize it. You only have to be able to recognize it and use it. So to help with the practice of this equation, I walked you through an example with the formula to show you how you could use the equation. So in this example, 2 kilograms of water with a specific heat capacity of 4,200 joules per kilogram degree Celsius changes temperature from 10 degrees Celsius to 100 degrees Celsius. The equation requires you to multiply together the mass, specific heat capacity, and change in temperature, which is 2 kilograms times 4,200 joules per kilogram degree Celsius times the change in temperature of 10 to 100, which is 90. So the total that you should have got is 756,000 joules of energy. Now back on slide 3, I gave you the definition of specific heat capacity, which is the amount of energy needed to raise the temperature of 1 kilogram of substance by 1 degrees Celsius. This slide was your turn. You had seen an example, so you could work out the missing information. Mass was 3 kilograms, specific heat capacity in brackets here was 4,200 again, and the change in temperature this time was 5 degrees Celsius. So 3 times 4,200 times 5 equals 63,000 joules of energy. Slide 8 was a recap of the keywords that we've used in the past to describe the changes of state. Melting is when a solid turns into a liquid. Evaporation is when a liquid turns into a gas. Solidifying or freezing is when a liquid turns into a solid. Condensing is when a gas turns into a liquid, and sublimation is the process of a solid turning straight into a gas without a liquid phase. These definitions are on page 193 in your revision guide. This next slide was a visual. Could you recognize a change of state with visual clues? So on the left, we've got melting chocolate and boiling water. On the right, condensation on a window and a frozen snowflake. Okay, so slide 10 took you to the PhET website where you could investigate what happens when you add energy to a system. So here I've got a solid mass. Although it does seem to have, let me just cool it down a little bit, make it a bit more solid. There we go. Okay. So I gave you some questions to consider. When a change of state takes place, will the mass change? So the answer is no. There are the same number of particles and the particles themselves have not changed. So the mass will be conserved, which is a fancy way of saying it stays the same. How are the bonds between particles affected? So if I add a little bit of heat to this, to the solid, you can see the particles eventually gain enough energy in their kinetic energy stores to break the bonds that are holding them together. If I continue to heat it, you can see the bonds are breaking. There's one that has escaped. Once they gain enough energy in their kinetic energy stores. They can break the bonds that hold them together. But if you cool the substance back down, then energy is lost and those bonds are formed. Okay, so you can see it's all to do with the energy and the bonds. What happens to the movement of particles? So heating the system transfers energy to its particles. They gain energy in their kinetic energy stores and they will move faster. So if I heat this up, the particles will move faster. If I keep heating it, they will get faster and faster and faster. Okay, the gases start slowly, but then they will move faster as well. A final question: what happens if you cool a gas down? So if I switch this over to gas and I cool it down, okay, you'll see that state changes can also be caused by cooling. The particles lose energy, they form bonds, and this is what causes the change of state. So there you go. And it's back to being a solid. So you can cool gases right down into their solid form. Okay. Slide 11 had a video showing you how I set up an experiment to show the change of state from a solid called stearic acid. So if you didn't watch this the first time around, it is now public on my YouTube channel for you to catch up. I asked you then to plot the results from my experiment on a graph. It wasn't all of the results, but it showed the part where the change of state was taking place. Pretty much all of you plotted these points without a problem, but no one remembered the line of best fit, or the curve, in this case, the curve of best fit. This graph shows that when the stearic acid was changing from a liquid to a solid, energy was still transferring, but instead of changing the temperature of the stearic acid, it was being used to build bonds that were holding the solid particles in place. Flat spots on the graph indicate where the energy is being transferred by heating or cooling and not being used to change the temperature. This is shown on page 194 in your revision guides. So based on that information, the freezing point is the temperature where the graph leveled off and the energy was used to form the bonds, which you can see on this results table was at 70 degrees Celsius. So to recap, everything is made from particles and the size of the particles differ from material to material, but in all materials these particles are moving. The higher the temperature, the faster the particles move, and heavy particles will move slower than lighter particles. I asked you to read this text and highlight the answer for some questions. So why do particles have kinetic energy? Because the particles are always moving. Compare the speeds of heavy and light particles when they're at the same temperature. Heavy particles will move slower than lighter particles. We know that particles in solids, liquids and gases have kinetic energy because they're moving, but they also have potential energy because the particles are kept apart when they move. This goes against the forces that are trying to keep them together. Gases have more potential energy because the particles are further apart than liquids and solids. To work out the internal energy of a system, you would add all of the kinetic energy and all of the potential energy for each particle together. The bigger something is, the more particles it has, and the more internal energy it will contain. The questions on this slide was, why do particles have potential energy? And this is because when they move, they're kept separate from each other. What is the internal energy of an object? So it's the sum of the kinetic and potential energy for each particle in a system. So we moved on to some grade booster questions. So remember that these are designed to challenge your thinking and allow you to apply what you've learned to different situations. Describe the movement of the particles in a hot gas compared to a cold gas. Your answer should refer to the particles, not to the gas as a whole. So in a hot gas, the particles are moving faster. You could also say the particles have a higher speed or they have more kinetic energy. When a gas is heated, the kinetic energy store will increase. Now, there's a bath of lukewarm water next to a cup of coffee, and the coffee has a higher temperature, which tells us that the particles it contains are moving faster or have higher kinetic energy than the bath. So this is similar to the first question about the hot gas and the cold gas. Okay. Why does the water then have a bigger internal energy store? This is because the bath water has a larger mass and therefore many more particles. If you add all of the kinetic and potential energy together, the total energy will be bigger than the coffee. Slide 22 stumped the entire class. Why does ice have less internal energy than the same mass of water at the same temperature? The melting point of ice is 0 degrees Celsius. So if we had a graph, this would be the point where the graph plateaued and the energy would be used to break bonds. Despite both being at 0 degrees Celsius, so having equal amounts of kinetic energy, for the change of state to have happened, more energy has been transferred to the water to melt it, so it must have more internal energy. This graph caught a few of us out too, because we were trying to label a point rather than a phase. You can see that I've used colours to show that the changes are gradual. The change of state isn't immediate. You can revise this more on page 194 in your revision guides. I know that I am incredibly proud of how hard you are working at these online lessons, and I hope that you are proud of yourselves. If you know that you can do more, it's not too late to turn it around. I will see you in the last live lesson before half term this Friday.